Hello class. So today we're going to go ahead and graph these rational functions. So I'm going to go ahead and do example number 6. And I can see here that I have a polynomial in the numerator and a polynomial in the denominator. So the first thing I want to go ahead and do in order to help me sketch is find these characteristics such as discontinuities. So let's go ahead and factor this real quick. The numerator is already factored for me, x plus 2. And the denominator is x squared plus x minus 2. I'm going to go ahead and factor this using the tabular method. So I'm going to go ahead and do this real quick. And that tells me that inside here, I go ahead and get the first term, x squared. Then I go ahead and see the next term. The last term is negative 2, so that goes right here. Okay, I go ahead and multiply those together. I get negative 2x squared. Now what I want to go ahead and do is find the number and another number that multiply to go ahead and give me this term right here, positive x. So two numbers that multiply to negative 2x squared. So obviously I have to have x. X times x gives me x squared. And I need to get that negative 2. So one of them has to be a 2 and the other one has to be a 1. Now they need to add up to a positive 1. So I'm going to go ahead and keep this one as a plus and this one as a negative. Okay. So let's go ahead and continue. I'm going to go ahead and compare what these two terms have vertically. What do they have in common? This is x squared. This is x. So they have x in common. These two terms right here, this is a 2. This is a negative 2. They have a 2 in common. These two terms horizontally on the top, they have an x in common. And these two terms horizontally at the bottom have a negative. And then nothing else is in common, but it will be a 1. Because everything is divisible by 1, so everything has a factor of 1. So in reality, this is broken down as x minus 1, right? The first two terms. And then x plus 2. Okay, so that's how I was able to factor the denominator. You can use other methods, even the quadratic equation, to find these factors. That was just the method that I preferred for now. Let me go ahead and make myself some little bit more space and find out the discontinuities. So for the domain, I'm going to be all real except when something occurs. Well, that something is either going to be a whole or vertical asymptote. And I can go ahead and see these terms right here, the factored form of the denominator, this x minus 1 and this x plus 2. Now, I can divide anything by any number except when I have 0. So what is that number? Right, whoops. What is that number here? What is this number x that will go ahead and give me that discontinuity? So let's go ahead and see x minus 1. So what will make this 0? Well, a positive 1. X equals positive 1 will make this equal 0, and I can't divide by 0. Okay, now the next one, x plus 2. X plus 2, I can go ahead and make that equal to 0, and I can find out what will give me 0. X equals negative 2. So when x equals negative 2, I have another discontinuity. So what I want you to know is that you're finding these x's right here that make the denominator 0. Okay, now that I have I can be any number in the world except x equals 1 and x equals negative 2, I'm going to decide, are these vertical asymptotes? That's a discontinuity in my domain. And wholes, that's also a discontinuity in my domain. Well, according to our notes, we can go ahead and see that in order for it to be a whole, the same factor has to be in the numerator and the denominator. So let's go ahead and check our factors. In my numerator, I got x plus 2, and the denominator, I got x plus 2. So can we go ahead and see that they are the same factor? Let me go ahead and write it for you since it could be a little bit messy. My factored form of all of this, says that it is x plus 2 divided by x minus 1, x plus 2. Okay, hopefully that's easier to see that this factor is the same as this factor right here. So what I can go ahead and do is notice that they are equal to 1. So I have a whole at x plus 2 equals 0, x equals negative 2. Does that make sense to you? Because to me, I see x equals negative 2 as a whole, and in my domain, I have a discontinuity there, so that makes sense. So I have a whole at x equals negative 2. Okay, let's go ahead and check this x minus 1. Where the heck did this come from? Well, it came from my domain. It came from from a discontinuity in my domain, which is a discontinuity that occurred right here in my denominator, x minus 1. When I substitute a 1 minus 0, I get division of 0. So this is going to be another discontinuity, and it's a vertical asymptote at x equals 1. Okay, now the next thing that I want to go ahead and check is the degrees of these polynomials. So the degree in the polynomial above is right here. It is seen as degree of this x right here is just x. So the degree right here is just an x. And here in the denominator I got x and I got x, that is x squared. So the degree in the numerator is 1 and the degree in the denominator is 2. So that's telling me that if I want to go ahead and check horizontal asymptotes, my n is less than my m. So that tells me my denominator is increasing more rapidly than my numerator. So like our pizza example, what happens as I share my pizza with lots and lots of people? My slice eventually becomes 0. So I have a horizontal asymptote at y equals 0. Horizontal asymptote at y equals 0. Okay, let's go ahead and plot these points so far. Let's see what we got. Oops. Okay, or not. Okay, let me go ahead and get the information. Okay. Okay, there you go. Okay, vertical asymptote at x equals 1. So that is a little dotted line right here. That is my vertical asymptote here at x equals 1. Now I have a horizontal asymptote at y equals 0. So that is right here, a horizontal asymptote at y equals 0. Horizontal asymptote, vertical asymptote, cool. Now, in order to help us out a little bit more, we have a hole at -2. Let's go ahead and take care of that. To take care of that hole, to find out its location, we're going to go ahead and refer back to how we found it. So let's do a little quick review about how we found this hole at x equals -2. Well, if we go ahead and look back over here in our function, we saw that I found it by doing this right here. I noticed that there are some terms that went ahead and simplified to 1. Okay, so in this term specifically, I got the x plus 2, that gave me that whole, so I went ahead and simplified. What I was left over with was 1 over x minus 1. So if I get this value x that I found for my whole, this x position, I can find the y position by substituting the -2 into the x. If I do that and evaluate this function at f of -2, I obtain 1 minus -2 minus 1. That gives me -1/3. -1/3. I'm going to go ahead and erase all of this notes over here to give myself more space. So this is the x coordinate was this one right here. So it was -2, and my y coordinate was this one right here, -1/3. That gives me exactly where this hole's location is at. So at -2, I am at -1/3. So that looks to me -2, -1/3, something like this. This is a hole. Okay, now what I'm missing next is the x and y intercept. So let me go ahead and make myself some more space. And I can go ahead and find the x-intercept by getting my function and setting it equal to 0. So now we get our function. So that is x plus 2. And then we can go ahead and pick the factor form. I really don't mind. X squared plus x minus 2 equaling to 0, which we saw is the same thing as saying 0 over 1. We cross multiply. The denominator all of this times 0, any number times 0 is just 0, is equal to these numbers right here. X squared times 1 is just, x plus 2 times 1 is just this. So I'm solving for this. This will give me my x-intercept. X is equal to negative 2. So x is equal to negative 2. As a coordinate, this is written as negative 2 and 0. We plot that. Negative 2 and 0. Well, that looks odd to me because it's saying the x-intercept, this point right here, goes ahead and touches my x-axis. But let's look at our horizontal asymptote. So what I want to go ahead and do is notice that at this value right here, we have an asymptote. So we can't really actually touch the x-axis because of the horizontal asymptote. So that was an interesting value here. Okay, can we do the same thing with the y-intercept? Well, sure. Let me go ahead and make myself some room. The y-intercept can be found as evaluating the function at 0. So I get my entire function, which said it was x plus 2, x squared plus x minus 2, and I substitute 0. So 0 plus 2, 0 plus 2, 0 plus 2, 0 squared plus 0 minus 2 equals 2 over negative 2, which is negative 1. So y coordinates y equals negative 1, which we can write as a coordinate as 0, negative 1. Let's go ahead and plot that. See where it's at. Or not. Here you go. That means we have a point right here at x is 0, y is negative 1. Have something right here. Okay, so according to what we know from the behavior near the asymptotes, this function cannot go above because it is bounded right here because of that asymptote, right? So it's going to go ahead and continue going below. Okay, this function is connected to that hole, so it needs to go ahead and pass through there, but not go above. So it's going to go really close to this horizontal asymptote at y equals 0. Now, let's find out where the graph can exist, because we have two options. It could either exist right here, or it could exist right here. It can only exist in one of these two options, 1 or 2. But how can we figure that out? Well, all we have to do is experiment with some values. So this horizontal asymptote is at x equals 1, correct? Now, what I want you to go ahead and think is, we know what happens as the graph is is less than x equals 1. We want to find out what it is when it is greater than 1. So pick any number, honestly, as long as it's bigger than 1. Okay? So what I care about is the position. Is it above the x-axis or is it below? So I'm going to pick a number and I'm going to evaluate the function at this number. Okay? So I like the number 1000. Okay, and I'm going to evaluate the function at 1000. So remember, I only care about the value, whether it is positive or negative. I don't care the exact value. Sorry. So the numerator, I add 2. So is that positive or negative? Let me write the equation. The equation is this one. So the numerator is the numerator will be 1000 plus 2. That is positive on the numerator. The denominator says 1000 squared. That's positive. Then I add more, another 1000, so it's gets still positive, and then I subtract 2. At the end of the day, guys, this is still positive. So positive divided by positive is positive. So this graph is telling me what? Is it above or below the x-axis? Well, if it's a positive, it has to be above the x-axis, so it should look like this. Cool. So this is our entire graph. So all we had to do, honestly, was notice. Can I zoom up? Notice that we had to go ahead and factor a little bit to find out our restrictions on our domain, like our holes and our vertical asymptotes. Then we determined if those holes or asymptotes we determined that these values right here were holes or asymptotes by checking our if they could be eliminated by simplifying. Then we went ahead and sketched it and checked the exponents for our horizontal asymptotes. Then we evaluated x-intercept, y-intercept using what we knew from the behavior of substituting for our y-intercept, f evaluated at 0, and our x-intercept, the function equaling 0. Oh, almost forgot the range. How can I go ahead and find the range, guys? Okay, so we're pretty much continuing to notice what the graph is doing. So how low does this graph go? Well, the graph, as we can see, has this part right here that's telling us that this is going towards negative infinity. So our range should start off with negative infinity, and it's going to go all the way up, but there's a hole right here. Right here there's a hole, and we found out that that height of that hole was negative 1/3. Okay, it will go ahead and continue going, union negative 1/3, after it continues the hole and go all the way to 0, and then we'll go ahead and continue from 0 all the way up to infinity, from 0 to infinity. Pretty cool, right? So that's how we're going to go ahead and graph these functions. Okay, thank you. Bye.